Hello my dear students of grade 10. Welcome to today's lesson, that is turning effect of a force. This is the 11th unit of your grade 10 science textbook. So as you can see, it is a physics lesson. So it's related to force, and force is a quantity. You all know it's a vector quantity. So it has a direction as well as the magnitude. Normally we are familiar with the different effects of force. So, how do we apply force? Either by a push or a pull. So far we have been using this force to make object move in a certain direction or undergo a linear motion. But in this lesson, we are going to discuss the turning effect of force. So, when we say turning effect of force, you can think of the rotating movement that is generated due to the application of force. So, under this, we will be discussing two main topics. I will move on to that. The moment, or what we call as the moment of force. You are familiar with this example also, students. Say you are trying to open a door or close the door. You try to open a window, close the window, or even your book. When you are flipping the pages, there you can see the pages move in a kind of a circular path, or at least a half circle or a quarter circle. So there is a turning effect. That is caused by the way we apply the force, and that gives rise to moment. We will discuss what that is. And when two moment of forces are coupled together, we get the couple of forces. So those are the two main topics that we will discuss in this lesson. With that, students, I will move on to the lesson. The next slide. We have seen that by applying forces on objects, it is possible to do the following activities. What are the following activities? Can you think of some? You can push an object, you can pull an object, or you can even lift an object up. So those are different functions that you can do. We have seen that by applying forces on objects, it is possible to do the following. So we can push an object, we can pull an object, or we can even lift an object. So when we say push, pull, or lift, now you are familiar with these examples. We apply a force, let's say 10 Newton force towards this direction. And when there is a resultant force, we have discussed that in the previous lesson, one of the previous lessons. So you know what resultant is. And due to this resultant force, the object moves. Resultant force. And due to that, there is movement in the object. So that can be caused by push, pull, or it can lead to lifting of the object. So those are the common things. Now I am going to discuss the turning effect. So as I told you, if it is a textbook, when you are opening the textbook, you know one side is all fixed. The pages can be flipped from only one side of the textbook. So when you flip the pages, you can understand the turning effect. A similar thing, the door at home or in your classroom. When you open and close the door moves in a turning manner. That is what we call as turning effect of force. So we will try to understand that. To understand that, we will first look at an activity. So here, let us do the following activity in order to investigate the factors affecting the rotation of an object. So here we are going to understand what factors give rise to rotation of an object. So this is the object here. The door is the object and we are going to rotate the door. You all know what hinges are. Hinges are the parts that help to fix the door to the frame. So the door does not come off the frame, it's fixed to that point, and there is an axis. So along this axis, you can imagine there is a line going along the hinges. So that is an axis, and the door is going to rotate along that axis or around that axis. That is what we are going to observe. Then to understand this moment of force or moment, what we will be doing is like this. You can see the points here, A, B, C and D. We fix rubber suckers to those points, each one 15 centimeter apart. Starting from the hinges side, or you can start from here. You can fix the value as say 15 centimeters, or if it is a broader door, you can make it 20 centimeter difference between the points. But there has to be a certain space between the points. So, and the spaces, if they are equal, then it would be more better to compare the results. Then what we do is, we start with point A. We connect the hook of the Newton balance to the hook of the rubber sucker, and we try to pull the door open with the minimum possible force. And we get the Newton balance reading when the door just starts to move. You have to have it closed but not locked. From that same position, when you pull the Newton balance, it should just start to move. And we note down the value. So here, mark 4 points A, B, C and D on the same horizontal level of a door attached to its frame by 2 hinges. So here, the door has to be attached, so it's not moving on that side. It can only move from this end, and we mark the 4 points, and they have to be at the same horizontal level of a door. So this slide, this has to be the same level. The length from here to here has to be the same. So it's the same horizontal level. Attach a Newton balance to the point A with the aid of a rubber sucker. So here first we use point A with the aid of a rubber sucker clamp and apply a perpendicular force on the door to open it. So if the door is in this plane, we will be applying the force this way. So that is going to be a perpendicular force. So here you can see, apply a perpendicular force on the door to open it. So you all know, students, force is a vector quantity, so the direction matters. Always if we apply a perpendicular force and then the lines, they are all on the same line, so the distance is the same. If you have one point here, another point here, that can have an effect. So here we remove all those effects by having all the points at the same horizontal level, and always it's going to be the perpendicular force. So the door has to move this way. It has to rotate in that manner. Then measure the force necessary to slightly move the door. So as I said, as it just opens or slightly move the door. You don't have to pull it open with a very heavy force or very high force. It can slightly move using the Newton balance. So measure the force necessary to slightly move the door using the Newton balance. Repeat this procedure for the other 3 points B, C and D and record your measurements in table 11.1 given below. So the table is in the next slide. So can you all understand what we are trying to do, students? This is what you do every day at home. But here we are trying to understand it by getting readings of the Newton balance. So then that is the activity. Now I am not going to do this activity in the lab because at home also you have done this. You might have had experience. You normally have the knob on this side of the door towards this edge of the door. So it's easy to open and close the door. But by chance, if you have ever tried to open or close the door from the space that is there between the door and the frame, that is holding the door maybe closer to the hinge. One thing, you can damage your hand, you have to be careful of your hands, but at the same time you would have known that it's very difficult to pull it close or pull it open. That is because at least to move it here and there, it's very, very difficult. That means if we want to open the door easily, we have to hold it at a certain point to make it more easier to move the door. That is what we are trying to understand. So since you have an idea as to what we have to do, I am not doing this activity. We will discuss the outcome with some observations. So, I will move on to the next slide. So, this is a table that you need to fill in, students. Now, if you look at the first column, point attached to the Newton balance, that is A, B, C and D. Those are the 4 points that you need to have. Then the perpendicular distance from the rotation axis to the force. That is from the hinges to the point where you apply the force. If I go back to the previous slide, from here to here, this is the perpendicular distance. So, A has the longest distance. You can see B less, C even more less, and D is the closest point. So, we have to measure that distance as well. So, if I move back to the slide, perpendicular distance from the rotation axis to the force. Then we have the Newton balance reading when the door just starts to move. I explained that to you all. When the door just starts to move. Then what we do is, we multiply the value of the force by the perpendicular distance. So, force has the unit newtons and the perpendicular distance we measure in centimeters, but we need to convert it to meters. The value of the force multiplied by the perpendicular distance will have the unit Newton meters. So, that is what I am going to fill now. Now, say we got values like this, for example. So, here when we have the Newton balance attached to point A, the perpendicular distance from the rotation axis to the force, let's say it is 40 centimeters. So, if it is 40 centimeters, you need to divide it by 100. That will be equal to 0.4 meters. If we divide this by 100, you will get the value as 0.4 meters. Then the Newton balance reading, let's say it's going to be 30 Newton. So, what will be the product? Value of the force 30 Newton into perpendicular distance. So, here it is going to be 12 and the unit will be Newton meters. Since it's given with the heading, I am not going to rewrite the units. Then we have point B. Point B, let's say it's 30 centimeters from the hinges. That is the rotation axis. From there to the point of application of the force, the perpendicular distance is 30 centimeters. So, again divided by 100, you get the value as 0.3 meters. So, 0.3 meters, let's say the force is 40 Newton. So, 0.3 into 40. What is the value? That is also going to be 12 Newton meters. The same way, if we take point C, let's say point C has a distance of 20 centimeters. Now, you can see it's becoming closer to the rotation axis. So, divided by 100, that's going to be 0.2 and the force will be 60 Newton. So, again you will have the value 12, 60 into 0.2. And finally, if you take point D, the point that is closest to the hinges, that if we take as 10 divided by 100, you will have the value 0.1 meters, here also 0.2 meters, and the force we will take it as 120 Newton. So, then again when you get the product, the value will be 12 Newton. So, now can you all see, students? We have the perpendicular distance decreasing. That means the point of application of force is coming closer to the hinges. And the force you can see is increasing. That's what I explained to you all. When you try to open or rotate an object closer to the point of rotation, you need to apply more force. Whereas if it is far away, say 0.4 meters, then you need to apply less force. But when you multiply the values, force into perpendicular distance, you always get the same value. Why? Because we are trying to open the same door. We are trying to rotate the same object. So to do that, not only applying force, but there needs to be a certain perpendicular distance. And the product of the force into perpendicular distance from the rotational axis to the point of application of force is what we call as moment of force or moment. There are two questions under this activity. We'll try to answer that. At which point was the force required to rotate the door a maximum? At which point? Now here you can see when it was at point A, 30 Newton force. As you go closer to the hinges and finally at point D, it's 120 Newtons. So at which point was the force required to rotate the door maximum? That's at point D. Point D. And the next one. At which point was the force required to rotate the door a minimum? That is point A. So there you can see point A. Closest to the hinges is point D. There the force is high. When it is far away from the hinges, then the force is less. So from that also you can understand how the distance affects the amount of force that needs to be applied. With that, students, I will move on to the next slide. So this is what we observed and this is what we can conclude. Now here you can see from A to this axis of rotation or where the hinges are, when the distance is more, force is less. And when the distance is less, force is more. And the product between the distance and the force is going to be the same value or a constant value for the same object. Those are the information that you can get from that activity. So if we write that, we can say force applied is high when the perpendicular distance between the point of application of force and rotational axis is less. So that is 1. If you write it the other way, force decreases when the perpendicular distance increases. Then the third point or the third conclusion that we got, what is it? The product of the force and the perpendicular distance is the same value. So the product of force and the perpendicular distance between the point of application and the axis of rotation. It can be the axis of rotation or maybe the point around which an object rotates. Axis of rotation. That is the term that we use to refer to that point. So, I told you all an imaginary line going along the hinges. That is the axis of rotation. So, the product of force and the perpendicular distance between the point of application and the axis of rotation is a constant. And so, what is the name given to this product? It is called the moment of force or moment. So, this product is known as moment, or you can say moment of force. And the ability of the door to rotate around that axis when you open or close is what we call as the turning effect. So then that is another thing that you need to remember. Ability of the force to rotate an object is known as the turning effect of force. So now can you all understand the topic, students? The lesson is on turning effect of force. So here by applying a force we are trying to rotate an object. In the activity it was the door. So there under that we discussed two types of turning effect, or we were going to discuss two topics. The first one is moment. So if there is an axis of rotation, if you apply force and if you make the object to turn or rotate, then that product between the applied force and the perpendicular distance between the point of application of force and the rotational axis or axis of rotation is what we call as the moment or moment of force. If I read that again. So these are what we understood from the activity. Force applied is high when the perpendicular distance between the point of application of force and the rotation axis is less. Then force decreases when the perpendicular distance increases. And then we saw that the product of force and the perpendicular distance between the point of application and the axis of rotation is a constant. And this product is what we called as the moment. So this product is known as moment or moment of force. And the ability of the force to rotate an object is known as the turning effect of force. Students, now you all have an idea as to what turning effect and moment are. Now we will try to understand the equation for moment of force and also how we can calculate moment of force and apply it in different instances. So then, here again, the picture is given to you to show you what happens. As I told you, this is the imaginary line, that is the axis of rotation. So you are going to apply the force. You are going to apply the force here. Say we pull the door open and that is going to be a perpendicular force perpendicular to the door. So the door is going to rotate this way. And that is the turning effect, and the product between the force applied and the distance, that is the perpendicular distance between the point of application. So here A is the point of application. A is the point of application of force. So between the point of application of force and this is the axis of rotation of the toe. That is what we call as the perpendicular distance. So this is the perpendicular distance. Perpendicular distance. And moment is what? Force into that perpendicular distance. That is why we got the unit as Newton meters. Force is going to have the standard unit newtons, and although we measure the distance in centimeters, we need to convert it to meters. So the unit will be Newton meter. Is that clear, students? So in order to subject a body to a motion in a straight line. So you're familiar with motion in a straight line. We discussed this at the beginning of the lesson also. When you push or pull or lift an object, the movement is the motion in a straight line. A force is required. In order to rotate an object around a given axis, what is required is not just a force, but a moment. So that is what we are considering here. A moment required to rotate an object is created by applying a force at a certain distance from the rotation axis. So here students, we have an object like this, let's say a door or a window, an object, and for this we need to have an axis of rotation. So when we apply a force, let's say we apply a pull, then what happens? The door is going to rotate. So this pull, the force has the ability to rotate the object. That's why we call it turning effect. And here there is the axis of rotation. And this is the point of application. Here we have the point of application. And for this force, we have a magnitude F, and the perpendicular distance between the axis of rotation and point of application of force, let's say this is D. Distance is D. So here F is force and D is the perpendicular distance. That is distance between point of application and axis of rotation. So there, you can see a moment required to rotate an object is created by applying a force. So we apply a force at a certain distance from the rotation axis. So here this is the rotation axis. This tendency for rotation due to the action of force is known as the turning effect of force. So that is what we are trying to understand here. This is how the turning effect works. So there has to be rotation and there has to be a distance between the axis of rotation and the point of application of force. So those are like the conditions that need to be satisfied when a force becomes the moment or the force giving rise to a turning effect. Is that clear to you all, students? So with that, I will move on to the next slide. Therefore, we can write an equation for the moment due to a force as follows. So now we are going to use the equation. So in that, I told you all F is the force applied and D is the perpendicular distance distance between the point of application and axis of rotation. Axis of rotation. So what is moment? Moment or moment due to force is equal to force applied into perpendicular distance between point of application of force and axis of rotation. So moment of force is equal to what? Moment is equal to F into D. F is the force applied and D is the perpendicular distance between point of application of force and axis of rotation. So this is something that you all have to remember, students. And then if we look at the units, we have already discussed that force is in newtons. The standard unit of force is newtons. And distance has to be in meters. So therefore, moment has a unit Newton meters. So SI unit or standard international unit of moment of force is equal to Newton meter. As an example, if we take an object, let's say a plank of wood, like that, and if it is fixed to one end by tightening it with a screw to the, let's say, another plank of wood or the table surface, and if you try to rotate this, say if you pull it this way, how is the plank going to move? It's going to move in this direction. What do we call that direction as? It is the clockwise direction. So if it moves this way, it's going to be the clockwise direction. Because of that, we are going to call it the clockwise moment. Now to the same object, we apply a force in that direction. Say here, if it is you are going to open the door, then you will be closing the door, opposite direction. Then how is it going to move? In this rotational movement. And that is the anti-clockwise direction. So therefore, we call this as the anti-clockwise moment. So students, you all know, we apply a force, we make the object to rotate. So that is the turning effect of force, and that is generated by the moment, force into perpendicular distance. And because of that, it has a unit Newton meters. And based on the direction in which the object rotates, if it is in the clockwise direction, we call it clockwise moment. Clockwise moment. Okay, students. So we have clockwise moment and anti-clockwise moment. We will try to look at it again. So when we apply a force of F at a certain point, that is at a distance away from the axis of rotation, and that is known as the perpendicular distance between the point of application of force and axis of rotation. So there it has to be the point of application of force. Point of application of force and axis of rotation. So then moment or moment due to the force that will be equal to force applied into perpendicular distance between point of application of force and axis of rotation. So their moment is equal to F into T. And the unit for force is Newton, unit for distance is meters. So therefore, the moment of force will have the unit Newton meters. That is the standard unit of moment of force. And then you saw that if it's going to rotate in the clockwise direction, it's going to be the clockwise moment and anti-clockwise moment depending on the direction in which we apply the force. With that, students, I will move on to the next slide. So since the moment is a tendency for rotation, depending on whether the rotation is clockwise or anti-clockwise, the moment too must be clockwise moment or anti-clockwise moment. So let's say, as I told you all before, we have a particular strip of wood like this, and if this part is fixed, so this side is the axis of rotation, we hang a weight or we apply a force from this point. So you know the plank is going to move in this direction, and that will be the clockwise moment. The same way, the same plank we fix the screw on this side. So here the axis of rotation is that. Then we apply the force from this point. Then what happens? The plank or the strip of wood will move in this direction, will rotate towards this direction, and that will be the anti-clockwise moment. If we have a strip of wood like this, and if we fix it in the middle. Now earlier we saw that both the nails or the axis of rotation were towards one end of the strip of wood. But now if we have it in the middle, you have seen this in your day-to-day activity also. And then if we apply a force in this direction, let's say force F, how will that rotate? It will rotate in the clockwise direction. So clockwise moment. At the same time, what will happen if we put or suspend a weight on this side as well? That is again F. What will happen to the rod there? It will rotate in the anti-clockwise direction, anti-clockwise moment. You all have seen this, students. Now, if there is a manual balance with a single beam, you have seen in the shops, they hold the balance up and into one pan, they put the weight. Then what happens? The side with the weight will go down. Let's say that is the clockwise movement. So, you can see the rotation. Then when they start, let's say we are buying potatoes. When they start putting the potatoes into the other pan, then what happens? Little by little, again this side goes up and the pan with the substance that we are buying again rotates. So, that will be an anti-clockwise movement. So, in the end, what happens there? Both the weights become equal. Let's say 1 kilogram weight and 1 kilogram potatoes, and the balance comes to an equilibrium. So, here we looked at direction for the rotation. So, from there we looked at the clockwise moment and the anti-clockwise moment. But in an instance where you have both clockwise and anti-clockwise moment, and if you can make them equal, then there will be a balance. Like how we have seen before also, if there is no resultant, there will be a balance. We will be discussing this in more detail again. But now I am going to discuss an activity where we look at the effect of force as well as the perpendicular distance from the axis of rotation to the point of application of force. So, for that we need to look at two activities. First, I will move on to the first activity. Investigation of the dependence of the moment on the magnitude of the force. So, to do this activity, we are going to try and understand how the magnitude of force affects the moment, or how moment depends on the magnitude of force. So, to do this activity, here you can see, students, these are the materials that we need. So, here we need a strip of wood, it has to be a fairly long one. So, a strip of wood. Then we need two washers. You know why we use washers? That is to fit the screw nut so that it doesn't really get stuck to the wood. It will allow the wood to move, but not very freely when you tighten the screw nail. So, here we need the screw nail as well. Screw nail. Then we need the Newton balance. So, we need the Newton balance, a drill, and then to fix everything, to keep the setup and do the rotation or observe how the rotation occurs, we need to have a table, or you can even have a plank of wood on top of the table. So, here we need a table and I will say plank of wood. So, what we can do is, on the surface of the table, it has to be a horizontal table. We place the plank of wood. To that, we can fix the strip of wood from one side only. So, that is using the screw nail and the washers. To do that, we need to first make a hole. So, we need to put a hole at one end of the strip of wood, and there needs to be other holes as well. So, to do that only, we need the drill. So, these are the materials that are needed, students. We will see how we have to do this activity. This is the method. So, here you can see this is the table surface, or you can have a plank of wood that should not move around. It has to be stationary. And then what we do is, we fix one end of the strip of wood or thin plank of wood, and you can see it has to be somewhat long, and that is fixed using the screw nail and using the washers so that it can rotate like this. Then what we do is, we calibrated. Here you can see calibrated strip of wood. Calibrate means, now here we measure the distance from this screw nail to this point. It has to be about 15 centimeters. You can decide that value. Here we have taken 15 centimeters. So there, from this point to this point, it has to be 15 centimeters. Then from A to B, there is a space of again 15 centimeters. So the distance from the screw nail to point B is going to be 30 centimeters. So screw nail to point C, it's 45 centimeters, and screw nail to point D, it's going to be 60 centimeters. And between each point, there is a difference or distance of 15 centimeters. That's how we have this strip of wood. Then what we do is, we have to fix a Newton balance. Say we can even start by fixing it to point A, and you try to pull the strip of wood, and as it starts to move. So if it is like this, if it just slightly moves, we take the Newton balance reading. You will see when you fix the Newton balance to point A, you will need to apply a very higher force. We have seen that with the activity with the door. But when you go away from the screw nail, because through the screw nail only, we have the axis of rotation. The strip of wood is going to move this way, or if we pull it the other way, it will move that way. But the axis of rotation is going to be through the screw nail. And from here to here, or from here to here, any point is going to be the perpendicular distance between the axis of rotation and point of application of force. So when that increases, you have an understanding, you know that the force decreases. So here we are trying to understand how the magnitude of force affects the moment. So to do that, what we do is, initially we fix the Newton balance to point D, and then we try to move the strip of wood. As it starts to move, we take the Newton balance reading. And then what we do is, we tighten the screw by half a turn. And again, we bring the plank back to the same position, the strip of wood back to its original position. Again, we try to pull it, and as it starts to move, we take the Newton balance reading. After doing that, we repeat the procedure after tightening the screw by another half a turn. So now we have done a complete full turn tightening. After that also, you have the Newton balance attached to point D. You pull it, and as the strip of wood starts to move, we get the Newton balance reading. So we will have 3 readings. The distance between the axis of rotation and the point of application of force is not going to change. Only the force will change. But we tighten the screw nail. Why is that? Initially, it was somewhat loose, initial stage. There, the ability to rotate, the turning effect depends on that tightness. So that has a certain moment. But when you tighten the screw by half a turn, the moment increases. Again, if you tighten it by another half a turn, the moment increases more. So by tightening the screw, we are changing the moment or the moment of force. And we get the reading of the force that needs to be applied. So we can understand the relationship between moment and the force applied. So that is the method. Let's look at the method again. Drill holes at points O, A, B, C and D, which are spaced 15 cm apart from the adjacent hole as shown above. So all the holes. Then next, clamp the stick to the table at the point O using the washers and the screw nail. And after that, so now attach a loop formed with a piece of wire to each of the holes at A, B, C and D on the stick. So you can either attach a wire and make a hole, you can tie a wire through the hole and make it like a loop, and to that you can attach the Newton balance, or else directly we can insert the hook of the Newton balance into the hole A, B, C or D and we can try to move the plank. Either way is okay, students. Then attach the Newton balance on the ring at D as shown in the figure. So here you can see, students, the Newton balance is shown to you there. So here you can see, students, this is the Newton balance that has been attached to the hole there, that is D. Then measure the minimum force necessary to barely move the stick, keeping the balance perpendicular to the stick. That is important. Minimum force necessary to barely move the stick. So as it starts to move, you take the reading and the balance has to be perpendicular to the stick. So it has to be perpendicular like that. That's how you have to apply the force. The axis of rotation in this case is the axis passing from the center of the nail head down through the nail. So axis of rotation is the axis passing from the center of the nail head. So that is what we will be taking as the axis of rotation. So here is the axis of rotation, here is the point of application of force, and that's going to be the perpendicular distance. You can remember, students, that is 60 centimeters distance and it's marked there as well. So you know the distance. Next, rotate the nail half a turn to tighten the stick a little more and measure the force required to slightly move the stick. So we repeat the activity. Again, rotate the nail half a turn to tighten the stick further and measure the force required to slightly move the stick. Tabulate your measurements. So that is what we have to do now, students. I am sure you know how to do this activity now. So we will go to the lab and do the activity. Okay, students. So now we are going to illustrate or try to understand the relationship between the magnitude of force and the moment of force. So before we go into that, what we will do is, you all know the setup here. We have the board and to that another board is a plank is attached, and to that you can see a thin plank is attached to it. All these are wooden planks. And then you can see the different points A, B, C and D. And this one is the nut which we are going to use to tighten and increase the magnitude so that we can observe the magnitude of the force that is needed to rotate this plank. And from this will be the axis of rotation, that is the nut here or the screw here, and starting from there. So from the screw to point A, it's going to be 15 centimeters, then to point B, it's 30 centimeters, C 45 centimeters and D 60 centimeters. So that's how the distance is going to be. First, we are going to understand how the moment of force works. So to do that, what I will do is, I will first attach this is the normal state of the screw. First, we will attach the Newton balance to point A. And as the plank starts to move, slightly move, you will have to get the reading of the Newton balance. So this is where we connect the Newton balance. So here I have marked the lines there so that you can see as the plank moves what the reading is. And we have to have the balance above the board. It shouldn't be touching the board. It has to be above the board. So you all know what to do now. Right. So if I try to pull it, so when I pull, you all can see, students, when it is 2 newtons, the plank just starts to move. So then what we do is we bring it back to the original position. Then I have to move the Newton balance to this nail. We can either use nails or, as shown in the book, we can tie a loop around the plank. We can mark the points A, B, C, D. And then we can place the loop at that point, connect the Newton balance to that and pull as well. So now the distance is 30 centimeters. Again, if I pull, you can see it's at 1 Newton force. The plank is moving. If we try again, when it comes to 1 Newton force, the plank is moving. Then the third one. That's point C, 45 centimeters away. So now here it's 0.6 newtons. Repeat again, 0.6 newtons. Then we move it to point D. So here it's 0.4 newtons. If I do it again, repeat again, it's 0.4 newtons. So can you all understand, students? When the point A was used, the force that we needed to apply was 2 newtons. And as we moved away from the axis of rotation, that is the screw, you know the perpendicular distance increases. This is the perpendicular distance. As the perpendicular distance increased, you were able to understand that the magnitude of force decreased. But when we get the multiplication, you will see the magnitude of moment of force will be the same value. Is that clear to you all? But in this activity, we are trying to understand how the moment of force or moment depends on the magnitude of the force applied. So to do that, what do we need to do? We need to tighten the screw. So it was the initial position here, and then you know we have to tighten the screw by half a turn. So I am going to do that. So now it has become tighter. Then we will use 1 point only. So to understand that, I will use 2 different points, the closest point A and the far away point D. So with point A, we will try. Now earlier you all can remember, students, it was 2 Newton force. Now when I try to pull, you can see when I apply a force of 3 Newtons, it's starting to move, just about starting to move. So that's 3 Newton. Earlier it was 2 Newtons, now it is 3 Newtons. The same way I will try for point D. You can remember, students, earlier at point D it was 0.4 Newton. So now we will try and see. So here we will look at the reading. It's moving when the balance is 0.9 Newtons. So can you all understand the relationship, students? When we tighten the screw, again the amount of force or the magnitude of force that was needed increased at point A as well as point D. So then again I am going to tighten it by another half a turn. Okay, so again I am going to use point A, and now we will try to move it and see. So here, so if I try to move it, you all can see when it comes to a reading of 4 Newtons, the plank just started to move. So that is the third reading. Initially we had 2 Newtons, then we had 3 Newtons, and now 4 Newtons. The same way, if we use point D there, you can remember initially it was 0.4 Newtons, then it was 0.9 Newtons, and now we will try to move it from the same point. Now can you all observe, students? When it comes to about 1.5 Newton, you can see the plank just starts to move. So from these, I am sure you all can understand that when the distance increases, that was not our intention, but you all were able to understand when the perpendicular distance from this point of axis of rotation increases, the magnitude of force decreases. But we wanted to understand that the moment of force depends on the magnitude of the force applied. So at point A, you were able to understand when we tighten the screw by each half turn, the magnitude increased. The same way at point D also. So from this, we can conclude that when the moment of force increases, the magnitude of force that needs to be applied has to be increased when the perpendicular distance is a constant. Okay, students. So you all got a good observation of how the forces change when we tighten the screw nail. So why did we tighten the screw nail? In order to change the moment or moment of force. So we had the initial setup. Then after tightening the screw by half a turn, and again after tightening the screw by a full turn. What did we get as the observation? That is the Newton balance reading, that is the force. So the initial force, that was 0.4 Newton. Then after that, when we tightened the screw by half a turn, what was the Newton balance reading? That was 0.9 Newton. And again, after tightening it by another half a turn, that is tightening it by a full turn, the Newton balance reading was 1.5 Newton. So you can see when we tighten the screw, that is when we increase the moment, the force increased. But all this time, what was the perpendicular distance? The distance between the screw nail and point D, that was 60 centimeters. Did that change? No, there was no change in that. So perpendicular distance was equal to 60 centimeters. So you know, students, that did not change. Then from these observations, what can we conclude? You can say when the moment increases, the force that needs to be applied has to increase, or the other way around, you can say when the force applied increases, the moment of force or moment will increase. So how does this work? Say you have a light door and a very heavy door. From the same perpendicular distance, if you are trying to open both the doors, you will need to apply a larger force to open the heavy door, whereas you need to apply a less amount of force to open the light door. That is why we change the moment of force. So depending on the object, you might have to change the amount of force that needs to be applied. But from this, what we can conclude is when the force increases, force applied increases, the moment of force increases, or when moment of force increases, the force applied needs to increase. So that is what we need to write as conclusion. So when the moment increases, the force applied increases. Or you can say when the force increases, the moment increases. So that is the relationship. Force increases, moment increases, force decreases, moment decreases. Okay, students. So now in this activity, you all would have understood the relationship between the magnitude of force and the moment of force. So we will discuss another activity where we look at the relationship between the effect of the perpendicular distance from the axis of rotation to the application of force on moment. So then I will move on to the next slide. Activity: investigation of the dependence of the moment on the perpendicular distance to the force from the point of suspension. So to do this activity, these are the materials that we need. We need to have a strip of wood or plank of wood. We need a strip of wood. We have used this in the previous activity also. Then we need washers. You all know we use the washers to fix the screw nail to the strip of wood. So we need screw nails, or actually one screw nail is enough. Then we need the Newton balance. Newton balance. Here we need the drill to drill the hole, and also we need a table. A horizontal table which has a smooth surface, and normally we can place another strip of wood on this table, and to that we can fix this strip of wood as well. Otherwise, we can directly fix the strip of wood to the table. So again, this is a similar activity like the previous one. If we have that setup, we can use the same setup as well. So now I'll explain the procedure to you all. The method, this is what we are going to do. So as we did before, you can see here students, this is the screw nail. So that is going to be the axis of rotation. Axis of rotation. Then we have the strip of wood. Like we did before, we have the points marked A, B, C, D, and you all can see the distances 15 centimeters, 30 centimeters, 45 and 60 centimeters from the axis of rotation, or where we have the screw nail. And then what we will do is, initially we tighten the screw by half a turn and then full turn. So now we have to bring it back to its original position, the normal turn, and then what we do is we fix the Newton balance using a loop. You can see here, because in this activity we will have to move the Newton balance for some time until we get the correct reading. So to facilitate that, earlier I used the holes into which I connected the Newton balance. But here we need to have a loop made with a thread or a string. And then what we do is, we have the Newton balance at the point A mark. And what we do is, we apply a force. And when we apply the force, we have to observe the strip of wood. And as it starts to move, we need to get the Newton balance reading. And that reading is going to be the F1 force. So this is the initial tightness of the screw. So that is actually somewhat loose. So it will be easy to rotate the strip of wood. Then what we do is, we turn the screw nail by quarter turn. So we are tightening the screw. So what do we do there? When we tighten the screw, we increase the moment of force. We are increasing the moment of force by tightening the screw. Then what we do is, without changing the force F1. Let's say if you get force F1 as 10 Newton, then what we do is, again we try to apply 10 Newton force and we try to move this strip of wood. You will understand that we cannot move this strip of wood. Why is that? Now the moment of force has increased. So then what we do is, we have the same value, but we move the Newton balance towards point B. So when you keep on moving it little by little and you try to pull the strip of wood, and you have to come to a point where the strip of wood just starts to move. Let's say when the Newton balance is somewhere here. With the same force F1, that is, I said if it's 10 Newton, the strip of wood starts to move. Then you measure this distance. So the first distance has been marked as x1, that is from the nail to point A. The second distance is x2. It can be here, it can be between A and B, or it can be closer to C, that doesn't matter. So you find the distance. Then again, you tighten the screw nail by another quarter turn and repeat the procedure without changing the force. The force has to be F1. You need to further push the Newton balance towards point C, and as it starts to rotate with the same force magnitude F1, you measure the distance x3. So you will get 3 readings, x1, x2 and x3. So x1 is anyway marked 15 centimeters and you have the force fixed value, that is F1. That is the method. Now again we will try to go through the method and understand the activity. Method. As shown in the figure, insert a loop made from a piece of thread around the stick of wood used in activity 2 near the point A and hook the balance on the loop. So this is what you have to do. You have to make a loop with a piece of thread that has to be inserted around the stick of wood that was used in activity 2. Here activity 2, students, you all know from your textbook the previous activity where we investigated the relationship between the magnitude of force and the moment of force. That was the previous activity. So the same strip of wood is used here. I told you all that. That is what is given to you as activity 2. And then we need to hook the balance. After that, rotate the screw by one turn to bring it back to its original position. I mentioned that it has to come back to its original position. In the previous one, we rotate the screw by 2 half turns. So it's 1 full turn. Then if we make it back 1 turn, it goes to its original position. Then find the force required to initiate rotating the stick slightly. Consider this as force F1. So consider this force as F1. So here what do? We find the force required to initiate rotating the stick. Slightly when the stick starts to rotate, we get the reading of the Newton balance and that will be F1. So throughout the activity, from this step onwards, we have to maintain F1 constant. We are not going to change the magnitude of force. Now rotate the screw by 1/4 of a turn to tighten it. Then move the loop together with the balance slowly towards D, keeping the force F1 constant. That is very important. Keeping the force F1 constant. When the stick begins to move around A, measure the distance x2 from O to the balance. So here we are going to measure the distance x2. So what is x1? That is the distance between the nail and point A. So that is what we take as x1. It was there in the diagram. You all can remember that. Repeat the procedure, tightening the screw by another 1/4 of a turn and sliding the loop towards D. Keeping the force F1 constant and measure the distance x3 from O to the balance when the stick begins to rotate around O. So here we are going to measure x3. So we have 3 perpendicular distances x1, x2 and x3 and we use the force F1 and we maintain it as a constant value. Why? Because there are 2 factors that affect the moment of force. One is the magnitude of force, other one is the perpendicular distance from the axis of rotation to the point of application of force. So here we are investigating the effect of the perpendicular distance. That is what we measure as x1, x2 and x3. So I am sure you all can understand this activity, students. So let's go to the lab and do the activity now. Okay, students. So now in this activity, we will try to understand the relationship between the moment of force and the perpendicular distance from the point of rotation to the application of force. So as you can see here, this is the screw nail. So that is the point of rotation or axis of rotation. And from there, if we get a certain point where we apply the force, the distance between the two is the perpendicular distance. So here again, I have a plank, a wooden plank that is fixed to the wooden board, and also it has been marked. Now from this point of rotation, point A, the distance is 15 centimeters. A to B, another 15 centimeters. So if you take the distance from the point of rotation, that is the screw nail, it will be 15, 30, 45 and 60 centimeters. So then what do? We have a loop here, that is a twine loop, to which I will be connecting the Newton balance. So when I connect it to this point, it has to be at the 15 centimeter mark, and then I will apply the force, and when I apply the force, we will have to measure the force that is needed to just make the wooden plank to move. So now I have the Newton balance fixed to point A. You can see that, students. I'm going to apply the force. So you can see I'm increasing the force, and as it comes to 2 newtons, the plank starts to move. So that is the force there. Then what I will do is I will tighten the screw a little bit. That is quarter turn. And then we have to try. Now see, if I apply 2 Newton force, there's no change. So what we do is we move this a little further away, still with 2 Newton, no change. Some more. Now it's moving, so I might have to try a shorter distance as well. Again. I will move it a little bit more. Now you can see when the force is 2 Newton, it's moving. So what we need to do is we need to measure this distance. The distance from the screw nail up to this point. So here, students, you all can see it's about 24.5 centimeters. So the distance has increased now. The force is the same, magnitude of force is the same, distance has increased. That is with quarter turn. So again, we have to increase the tightness by another quarter turn. So I have increased the tightness now. From the same point, if I apply 2 Newton force, there's no movement. Bring it to the 30 centimeter mark, still no movement. A little bit more. Now you can see it starts to move. So we will have to just adjust and find the correct point as we did before. So now at this point you can see still not enough. So I'll make it a little further from point B. Now when I apply 2 Newton force, you can see it just starts to move. So this is the distance. So here, if we measure the distance again, it comes to 32 centimeters. Is that clear to you all, students? So initially, students, we got the reading at point A as 2 Newton force. So that is the magnitude of force. Thereafter, we did not change it. So 2 Newtons, 15 centimeters. Then we increased the tightness by quarter turn. It became 24.5 centimeters. The same magnitude, 2 Newton force. And when we tightened it more, another quarter turn, now you were able to see the reading as 32 centimeters. Still the force is the same. So you can see, by tightening the screw, we increase the moment of force. But we have the magnitude of force fixed. Therefore, the perpendicular distance from the axis of rotation to the point of application of the force increases. So, can you all understand the relationship now? Okay, students. Did you all observe clearly what happened during the activity? I'm sure you did. So, when I tighten the screw nail, the perpendicular distance increased and we maintain the force constant. What was the force? It was 2 Newton. Initially we measured, or we know the distance x1, that is from the screw nail to point A, that was 15 centimeters. Then when the force was kept constant, the screw nail was tightened, you were able to observe that the perpendicular distance had to be increased. So first I will write down the observation. So here we have the initial setup, that is bringing back the screw nail back to its original position. The force required was 2 Newton and we measured the distance to the balance x, but here it was x1, that was equal to 15 centimeters. Screw nail to point A. Then with the force constant and after tightening the screw by quarter turn. So after tightening the screw by quarter turn, what is the force? the same magnitude, 2 Newton, and we measured x2. What was that? It was 24.5 centimeters. And then again, I tightened the screw by another half turn. After tightening the screw by half a turn again the force was 2 Newton, but we measured x3 and that was 32 centimeters. So from these observations, students, what can you all understand? We maintain the force constant. We increase the moment by tightening the screw, and with that, the distance, that is the perpendicular distance from the axis of rotation to the point of application of force increases. And that is the conclusion of the activity. So if I write the conclusion, when the magnitude of force is constant, the perpendicular distance from the axis of rotation to the point of application of force increases with increase in moment. Or in other words, what can you say? When the magnitude of force is constant, the moment of force will increase with the increase in perpendicular distance. So here we say the perpendicular distance increases when the moment of force increases. That is what we did during the activity. It can be the other way also. So if I write another conclusion, or when the magnitude of force is constant, force is constant, the moment increases with increase in perpendicular distance from axis of rotation to the force. So that is the conclusion. When the magnitude of force is constant, the perpendicular distance from the axis of rotation to the point of application of force increases with increase in moment. Or when the magnitude of force is constant, the moment increases with the increase in perpendicular distance from axis of rotation to the application of force. So from these two activities, students, you all can understand both factors, the magnitude of force and the perpendicular distance affect the moment of force, and both increase the moment of force. When they increase, the moment of force increases. So that is this chapter. We looked at what turning effect of force is, then we discussed what moment of force is or moment is, and the factors that affect moment of force. In the next chapter, again I will discuss the direction of moment, what we discussed as clockwise and anti-clockwise movement, and when both these act on one object, how we can maintain equilibrium, and also calculations related to that. Thereafter, we will discuss couple of forces.